Hello everyone. So I've been getting a lot of requests lately for some more review on rotation topics in particular. So I thought I would make a video where I go over a few example problems that highlight some of the different topics that showed up in that unit. The first one I think technically will be a review of some stuff we did in class, but the other two will have some new material. All right. So to start off with, let's look at the dynamics of rolling with friction. And in particular, we're going to look at some object that rolls down an incline with angle theta. So let's say this object has some mass m, maybe some moment of inertia I, and radius r. So we want to know how this is going to accelerate down the hill, assuming that it rolls without slipping. So it's good to remember what that means. Rolling without slipping means that the linear velocity and the angular velocity of the object are related in a particular way. It means the velocity is equal to the angular velocity multiplied by the radius. All right. So first of all, friction is going to be necessary for this to happen. If I just place an object on top of a frictionless incline, then there will only be two forces acting on it. If I drew those here, one force would be the gravitational force mg, and the other force would be the normal force, which would act in this direction. Now, these two forces alone are enough to cause the object to accelerate down the incline, but neither one will cause the object to rotate because neither one creates a torque around the center of mass of this object. Both of the forces go right through the center of mass. So in order for this thing to rotate, it would have to rotate counterclockwise as it rolled down the incline. There's going to have to be a friction force in this direction. All right, so those are the three forces here, and in order to solve for the acceleration of the system, we're going to have to write two equations, and both of those equations are versions of Newton's second law. First of all, let me define a coordinate axis here. So I'm going to make this my x-axis. So I'm going to measure the acceleration with downhill being in the positive direction. And to be consistent with rotation, I will make rotation in this direction positive. All right, so now I can start writing equations. So the net force acting on this object is equal to its mass times acceleration. This thing is only going to accelerate in the direction that's parallel to the incline. So I can ignore the normal force and the component of the weight that's opposite the normal force. Those will just cancel each other out. So I'm going to have two forces in the downhill direction or uphill. One is going to be the component of the weight that points downhill, which is mg sine theta. And that's because this angle up here is the same as the angle of the incline. So that will be in the positive direction, and then we have friction in the negative direction, so we subtract that, and that equals mass times acceleration. All right, so that's one equation, and we're just going to leave it in this form for now. The other equation we can write deals with rotation, and it says that the net torque is equal to I times alpha. So we have three forces here, but if we're measuring the torque, or calculating the torque, with respect to the center of mass of the object, the normal force and the gravitational force both generate zero torque. So the only torque is from friction, and that's going to be equal to F times R. All right, and that's because the friction is perpendicular to the radius of the wheel at that point. That's going to equal the moment of inertia times alpha. All right, so to couple these two equations, we need one more thing, and that's the relationship between A and alpha. And we actually get that relationship from the rolling without slipping condition. So V and omega are both going to be functions of time. They're not constant. So we can take the derivative of this equation with respect to time. The derivative of velocity with respect to time is acceleration, and the derivative of omega with respect to time is the angular acceleration. So that equation there is going to allow us to couple these two equations together. All right, so I'll start with this one. I can say Fr equals I times A divided by R, or the friction force equals I over R squared times A. If I plug that into the other equation, I get mg sine theta minus I over R squared A is equal to ma. Since I want to solve for the acceleration, I will move the middle term over to the right-hand side. And I can factor out the a while I'm at it. So I get acceleration equal to mg sine theta over m plus I over R squared, or if I divide the top and bottom by mass. All right. This is usually the preferred way of writing this equation because now the numerator is an acceleration rather than a force. So we see that the acceleration of the system is g sine theta. Remember, this is the acceleration that you would get with no rotation. And then the rotation of the object turns out to decrease the acceleration by a factor of 1 plus I over mr squared. And I over mr squared will end up just being a numerical constant, and that's going to depend on the shape of the object that you have. So if this was a hollow cylinder rolling down the incline, I would be equal to mr squared, so the denominator here would be 2, and we would get exactly half of the acceleration of a non-rotating object. However, if we had something like a sphere, where I is 2/5 mr squared, then our denominator would be 7/5, which means the acceleration would be 5/7 of g sine theta. So this is the more general form that shows what it is for any type of object. All right, so next let's look at a different type of rolling without slipping problem. So actually call this one the billiard ball problem. So the idea here is we have a billiard ball, or just some kind of round object, on a frictionless surface. And we want to strike this object with a horizontal force so that it takes off rolling without slipping. So we want the resulting angular rotation and the resulting linear velocity to obey the rolling without slipping condition. All right, so notice I've drawn this horizontal force somewhere above the midline of this object. If I applied a horizontal force exactly at the midline, then that force would generate no torque, since the line of action of the force would go through the center of mass of the object. This means with no torque from the horizontal force and no torque from friction, the object actually would not rotate at all. So we have to apply this force displaced vertically somewhat from the midline so that it causes rotation as well as linear motion. Okay, so first of all, we're going to solve this by actually dealing with accelerations rather than velocities. That's not right. Here we go. All right, so let's look at the geometry of this problem a little more first. So this force is acting on a horizontal line that goes above the midline of this object, and this is going to generate a torque. So that torque is going to depend on how far this line is from the center. So an important question becomes, what is this height here? Well, if this is the radius of the object, then this must be h minus r. So we'll come back to that in a second. Okay, so we can start writing our Newton's second law equations. F equals ma. Since there's no friction, the only horizontal force on this object is F, and that is equal to m times a. So there's really not much to do with that equation. As far as the rotation goes, the net torque is equal to I multiplied by alpha. So the torque is going to be the force multiplied by that distance from the center that we just determined was h minus r. That is equal to I multiplied by alpha, which is the same as A divided by R. All right, so let's put in something specific for the moment of inertia. Let's say this is a sphere, so the moment of inertia is 2/5 mr squared. That would make this 2/5 m r squared, but then I have A divided by R, so that gets rid of one of the factors of R, and I end up with this. All right, so in the second equation, I can substitute in force equals ma. So I get this, and then I can cancel m and a, and I get h minus r equals 2/5 times the radius, or h is equal to 7/5 times the radius. All right, so that tells us exactly how high up we need to apply this horizontal force to get perfect rotation with no slipping when we hit this object. So if you play billiards and you want to apply topspin or backspin to the ball, then that basically means you want to line your cue up either above or below this point to cause over or under rotation. That's a bit of a more advanced topic though, so I won't go into that. All right, if this was an object other than a sphere, the only difference in the derivation here would be this expression here for the moment of inertia. So you would basically get a different coefficient here, and we would end up with a different coefficient down here, but the rest of the analysis would all be the same. So if we had, say, a solid cylinder that we were doing this with, we would need to apply the horizontal force at a different location, and I think you should find that to be 3/2 r up above the horizontal surface. Okay, so there's one other thing that I wanted to go over here, and that was a problem that deals with calculation of moment of inertia for a non-uniform object. We did problems similar to this in class when we were talking about center of mass, but we have not derived moment of inertia for something like a horizontal rod with non-uniform mass density. All right, so let's look at that as the last example here. So here we have a rod with length L and a total mass equal to m, but it is not a uniform mass density. So the mass density is going to depend on where the mass is located. So let's make that a little more concrete. Let's put an x-axis here, and I will label the center of the bar x equals 0. So that makes this L over 2, and this minus L over 2. So let's say the mass density of this rod is given by a function, let's go lambda of x. So it's going to be a function of the distance from the center. And let's say this is proportional to x squared. All right, so let's look at two questions here. First, what is c equal to in terms of the mass and the length? And then what is the moment of inertia of this rod rotating around the center? All right, so the first question, what is c? We need some way of relating the mass density function to the total mass. So if we add up the mass of every tiny little slice of this thing, then we should get m. So let's imagine dividing this up into a bunch of little slices and asking what is the mass of this tiny little slice. Well, this mass density is basically telling us the mass per unit length. So if I call the mass of this dm, that's going to equal the mass density multiplied by the width of the slice, which is dx. So that means our mass density is equal to c x squared times dx. So if I add up the dm for all of these slices for the entire bar, then I should get m. So what that looks like in terms of an equation is an integral of dm over the entire length of the bar. Actually, I should not put in these limits yet. So what I need to do is transform this integral into an integral over the variable x by using the substitution that I just identified. And now x is going to range from minus L over 2 to L over 2. And what is this going to be equal to? Well, this is just the integral of x squared, which is x cubed divided by 3. And we're going to evaluate this between x equals minus L over 2 and L over 2. All right, so that gives us L over 2 cubed minus negative L over 2 cubed. Luckily, cubics are odd functions, so this will not be 0. We'll have L cubed divided by 8 minus negative L cubed over 8. So that ends up being L cubed over 4, or C L cubed divided by 12. All right, so how does this help us? Well, what we've just done here is integrating dm over the entire length of the rod. So we're basically adding up the mass of all of these little slices. So we just calculated the total mass of the rod. So this is equal to m, which means that C is equal to 12m divided by L cubed. So that's our answer to question 1, and that's going to be required to get the answer to question 2 as well. All right, so to find the moment of inertia, return to this little slice that I've drawn up in the figure. The moment of inertia of that little slice as it's rotating around the center, if we imagine spinning this entire rod around its center of mass, the moment of inertia, which we'll call di of this little slice, is equal to the mass of that slice multiplied by the radius of this path squared. But the way I've defined my x-axis, the radius of this path is just x. So if di is equal to x squared times dm, then the total moment of inertia will just be the integral of di over the entire length of the rod. All right, so I have to do this integral x squared times dm. I cannot do this integral as it's written because I've got mixed variables, but we already know that dm is equal to cx squared times dx. So we put in the same limits, and we're just doing essentially the same integral as before, but we have x to the 4th instead of x squared. All right, so the integral of x to the 4th is x to the 5th over 5. And if we plug all of this in, we should get c times L to the 5th divided by 80. Okay, so that is our moment of inertia. Now we would like this to be in terms of the mass and the length rather than c and the length, so we're going to substitute in our previous result for c. So c times L to the 5th over 80. All right, and that 12 over 80 will simplify a little bit. We can cancel a factor of 4. And then the L cubed will cancel 3 of the factors of L up here. So we get 3 over 20 times mL squared. All right, so this has the right units for a moment of inertia. It's a mass times a length squared. This numerical factor out in front just is a result of the mass density being quadratic. Notice the c ends up being canceled here. So the moment of inertia of this rod actually does not depend on the value of c. All it depends on is the fact that the mass density is quadratically dependent on the distance from the center. So this procedure could be repeated for any other type of polynomial mass density function, at least single term polynomial, so something like x cubed or just x or x to the fourth. You could go through this same type of derivation. The only thing that's going to change is the value of this fraction that you get out in front. All right, so hopefully you found those 3 problems somewhat helpful. If you have any questions about these or any other requests of types of problems that you would like to see, please let me know, and I will try to make sure I provide those as well. All right, thank you for watching.